with the ability to withstand 10,000 charging cycles, 5 times more than lithium-ion batteries, a remarkable energy density of up to 400 watt-hours per kilogram. This increase promises to open up the possibility of increasing the range of electric vehicles up to 350 kilometers on a single charge. Especially solid-state sodium-ion batteries, with energy density up to 10.8 A/2, twice that of conventional sodium-ion batteries. So how are these innovations booming the entire battery industry? Let's find out in today's episode. Recently, a research team from Cambridge University has developed a new electrode material for sodium-ion batteries called disodium rhodizonate compound, which helps increase battery charging speed by 30 times compared to conventional batteries. ABB company in Switzerland has created a sodium-ion battery that can withstand 10,000 charging cycles, 5 times more than lithium-ion batteries, helping to extend the battery's lifespan. In particular, the ability of sodium-ion batteries to withstand more charge cycles and have a longer lifespan can help reduce up to 50% the costs of replacing and environmental impacts associated with battery replacement and recycling. This represents a major step forward in improving the performance and efficiency of sodium-ion batteries, opening up great prospects for widespread application in areas such as electric vehicles and grid energy storage. How are sodium-ion batteries rapidly emerging as a game-changer in the energy storage landscape? While still under development, they boast several impressive achievements that position them as a strong contender to dethrone the reigning champion. Lithium-ion batteries. 1. Improved energy density. One of the most significant breakthroughs is the improvement in energy density. Sodium-ion batteries are now showing their potential in terms of densities between 300–400 watt-hours per kilogram. This represents a significant leap of starting point compared to the 100–265 Wh range of lithium-ion batteries. In simpler terms, a sodium-ion battery can store more energy in the same amount of space or weight, translating to a longer driving range for electric vehicles, or extended lifespan for electronic devices. In theory, the theoretical energy density of lithium-ion batteries can only reach 325 watt-hours per kilogram with the most advanced materials such as lithium-sulfur, Li-S. Researchers are working to improve sodium-ion's energy density with the goal of reaching 500 watt-hours per kilogram in the near future. Some studies also show that in the future, sodium-ion batteries can increase the operating range of electric vehicles by at least 30%, up to 450 miles compared to lithium-ion batteries. This could also have a positive effect on the electric vehicle market, as range becomes one of the most important factors consumers care about. The significant increase in range that this sodium-ion battery can provide and promote wider acceptance and use of electric vehicles in the future. This could also have a positive effect on the electric vehicle market, as range becomes one of the most important factors consumers care about. The significant increase in range that this sodium-ion battery can provide and promote wider acceptance and use of electric vehicles in the future. Moreover, scientists at the University of Maryland have developed a solid-state sodium-ion battery with an energy density of 10.8 ampere-hours per square centimeter, 2 times higher than conventional sodium-ion batteries. They have focused on optimizing the structure of sodium-ion batteries to achieve higher performance. So what else researchers can do to improve the energy density of sodium-ion batteries? Researchers are developing new electrode materials to more efficiently store sodium ions, which is key to improving energy density. Optimizing the battery structure is also a potential solution. Improving the sodium-ion battery structure to increase the contact surface area between the electrode and the electrolyte solution can also contribute to increased energy density. 2. Enhanced performance. The charging rate of lithium-ion batteries typically ranges from about 0.5 C to 1 C or higher. At 1 C, a lithium-ion battery can be fully charged in about 1 to 2 hours, depending on the battery's capacity and specific charging conditions. Previously, the charging speed of sodium-ion batteries was often slower than that of lithium-ion batteries. However, with recent progress in research and development, several studies have reported increasing the charging rate of sodium-ion batteries up to 5C. This means the sodium-ion battery can be fully charged in just a few minutes in comparison with at least an hour of that for a lithium-ion battery, reducing waiting times and increasing user convenience. According to Sodium's latest report, sodium-ion batteries can be fully charged to 80% capacity in 15 minutes. ABB's sodium-ion battery will be able to fully charge an electric bus battery in just 6 minutes. These are truly groundbreaking numbers for the electric car industry. More surprisingly, the new electrode material is disodium rhodizonate compound, which helps sodium-ion batteries increase charging speed by 30 times compared to conventional batteries. This represents a major step forward in improving the performance and efficiency of sodium-ion batteries, opening up great prospects for widespread application in areas such as electric vehicles and grid energy storage. As we just mentioned from the beginning, ABB company in Switzerland has created a sodium-ion battery that can withstand 10,000 charging cycles, 5 times more than a conventional lithium-ion battery, as lithium-ion batteries can only withstand 500, 2,000 charging cycles. It is estimated that sodium-ion batteries can maintain 80% of their capacity after 2,000 charging cycles, while lithium-ion batteries can only maintain 80% of their capacity after half as many charging cycles as sodium-ion batteries. 3. Minimize production costs. Scientists at the University of California, Irvine recently discovered a new sodium-ion battery production method that helps reduce production costs by 50%. According to Bloomberg NEF, the price of a 60-kilowatt electric vehicle battery using sodium-ion batteries could drop to $70 kWh by 2030, compared to 132 kWh for LIB batteries today. Besides, a UK company called Rhodizonate is developing a large-scale sodium-ion battery production process that promises to reduce battery production costs at least 30% to a level competitive with lithium-ion batteries. Furthermore, according to the survey, the global sodium-ion battery market is expected to reach USD 1.4 billion by 2028, with a compound annual growth rate, CAGR, of 45.4% during the period from 2023 to 2028. And it is expected to become more valuable at 11 billion USD by 2033. Investments in sodium-ion research and development are increasing rapidly and opening the door for developing production technologies and advanced methods to minimize the production cost and boost this process. For example, Natrion raised $66 million in 2022 to develop batteries for electric vehicles. Also this year, Natrion Company signed a contract with General Motors to supply sodium-ion batteries for its electric vehicles. A year later, ABB Company cooperated with ThunderSky to produce sodium-ion batteries for electric buses. These contracts not only open new doors for the transportation industry, but also help sodium-ion get closer to being the champion in the battery world. 4. Special structure and operating principles. Sodium-ion batteries have a similar design to lithium-ion batteries, meaning both are possible produced using the same methods. Both generate electricity through a chemical reaction and are made up of an anode, a cathode, a separator, and an electrolyte. But in sodium-ion batteries, lithium ions are replaced by sodium ions in the battery's cathode, and lithium salts are swapped for sodium salts in the electrolyte. Sodium, which is part of salt, needs to be chemically processed before it can become the material that goes into the cathode and electrolyte. Sodium ranks alongside lithium on the periodic table, meaning they are both very similar chemically. However, lithium-ion batteries use electrodes made from graphite for the cathode and metal oxides of nickel, cobalt, and manganese for the anode. During charging, lithium ions from the anode move through the cathode and are absorbed into the graphite grid. When used, lithium ions move back from the graphite through the anode, creating an electric current. Meanwhile, sodium-ion batteries often use materials for the anode and cathode that contain sodium. These electrodes can be made from materials such as sodium ferrite, NaFePO4 for the anode and graphite for the cathode. During charging, sodium ions from the anode move through the cathode and are absorbed into the graphite grid. When used, sodium ions move back from the graphite through the anode, creating an electric current. In terms of ion size and energy storage capacity, lithium ions are more compact than sodium ions, allowing them to move easily within electrode materials. However, due to its smaller size, lithium is also easily absorbed into protective layers or creates dendrites, posing a risk to battery safety and longevity. On the other hand, sodium ions are larger and can exert more stress on the structure of the electrode material. This can reduce the risk of creating dendrites and improve battery life. In addition, because sodium is easier to find and cheaper than lithium, using sodium ions also helps reduce battery production costs. The structure of sodium-ion batteries typically does not require careful selection of electrode materials like lithium-ion batteries. Currently, researchers are developing new sodium-ion battery structures that optimize charging speeds, such as using more conductive electrode materials and 3D battery designs that increase the contact between the electrode and the electrolyte. This makes sodium-ion battery research and development more flexible, with many material options available. The operational advantages of sodium-ion batteries over lithium-ion batteries include the ability to use a wider variety of electrode materials, lower manufacturing costs up to 50%, and high levels of safety and stability. This makes sodium-ion batteries an attractive option for future research and applications.